Saxon Algebra 1, Lesson 92. Oh, this is an exciting day, my students. We're starting work on a new type of word problem. They are very, very, very quintessential algebra problems. They're like iconic in the world of algebra, and whenever older people talk about, oh, remember back in algebra, they very often are thinking of this kind of problem. They are officially called uniform motion problems, but I don't like to call them that because those are big, creepy, hard-sounding words. They're not. These words actually make our problem easier because what uniform motion means is that people are traveling at a constant speed. That's what uniform motion means. That makes these problems much easier. In calculus, you'll learn how to work problems where people are traveling at changing speeds, right? Acceleration and deceleration, which is real life, right? Who goes on a trip in the car and goes at the same speed every single inch of the way, right? You're speeding up, you're slowing down, you're braking for lights, you're letting ducks cross the street, right? There's all kinds of interruptions. But in these problems, we're simplifying them and saying the speed's the same the whole time. What is fundamentally important is that we understand that distance equals the rate times the time. Now, you inherently understand this idea because you have traveled in cars your whole life and you understand the basic principles about the way it works. If your mom and dad each drive you from time to time to, I don't know, the movie theater where you go with your friends, it's the same distance. But like most families, one parent usually drives faster than the other. In our family, I drive faster than my husband. So the rate that I drive to the movie theater is faster, so I get there in shorter time. And my husband drives a little slower, so it takes him a few extra minutes to get to the movie theater. You probably understand this. You know that if you're going to grandma's house on the interstate, you're going to get there faster because you can travel. Your car can go faster on the interstate. If you take the back roads, going the same distance to grandma's house is going to take a little longer because you're not driving as fast, right? You naturally understand that. So that's what we're getting at with this expression, which can be summarized like this: distance equals rate times time. Now, in this first kind of problems that we're looking at, we're talking about very simple trips. I just described one of them. I drive to the movie theater. My husband drives to the movie theater. It's the same distance, right? And so we say that the first distance equals the second distance. But we can also change this into this form. And I'll tell you why we like this form in just a minute. I want to go back to this though. I don't want to talk anymore about me and my husband driving to the movie theater. That's boring. What I would rather talk about is the movie Lord of the Rings. I hope you've seen Lord of the Rings. In it, you know that a little dude named Frodo has a golden ring that is evil, and it needs to be taken to the mountaintop and thrown into the fiery lava that burns inside the mountain so that it is consumed by fire and no longer causing trouble in Middle-earth. So our friend Frodo leaves his happy green homeland, the Shire, and he travels to the top of that mountain. But he does not go alone. Oh no, he does not, because his fellow hobbit and dear friend Sam takes it upon himself to go with him. So Sam also leaves the Shire and travels all that way to the top of Mordor and is right there at Frodo's side when the ring is pitched in to the fiery lava. These guys have a trip that matches exactly to what we're talking about. Now there's another kind of trip that also works this very same way. It's a trip with equal distances, and that also involves Sam and Frodo. In this picture, Sam and Frodo travel, like I said, from the Shire to the mountaintop, but then they turn around and they come all the way back, right? Now, they don't travel in exactly the same method, right? They have to walk most of the way there. I think they ride on horses at the beginning a little bit. No, I guess the horses are chasing them, but on the way back, they get a ride from some eagles, don't they? So that cuts off a lot of their journey by time, but they're still making the same trip. So this also fits this same pattern, right? So I call this style of problem, and we're going to learn other styles, I call this the Lord of the Rings style. And when we see the other kinds, you'll understand how they're different. Right now, you're thinking, what are you talking about? But when you see the stories are different in the other kinds of problems. This is how we can make sense of the stories as they're given to us in the book. We'll be able to see this kind of picture emerge. We'll be able to translate our picture into this expression, this equation. The reason it's important that we go from here to here is that John's going to give us some information and ask us to solve for others. He's going to give us rates and times. So in order to use the information in the book properly, we need to have this form of the equation. Okay? And when we solve one, you'll understand how that works. This is what we call the base equation. For our Lord of the Rings style uniform motion problems. Okay, let us try one. And I want to start it here so you can see these notes as we carry on. Let me read you a story. On Tuesday, the express train made the trip in 12 hours. On Wednesday, the freight train made the same trip in 16 hours. Okay, so what we can see is that we have the same trip, one an express train, one a freight train. And because of the times we live in, you might not know the difference. Express trains, by definition, an express train means it skips a lot of the stops and it goes faster. It usually is carrying people that want to go a long distance, so it skips over the closer stops and just keeps on sailing out of town and goes on a longer trip. A freight train is loaded down with cargo, and it typically stops at every stop and travels at a much lower speed because it's kind of bumbling along full of heavy things. So this is the distance of the express train, and this is the distance of the freight train. They're making the same exact trip on different days. Now, all I have done is read the story and drawn a little picture that seems to fit with the situation in the story, right? Let me read it again. On Tuesday, the express train made the trip in 12 hours. I'll take care of the hours later. Don't worry about that. On Wednesday, the freight train made the same trip. That's the picture. Now, before I get into all those details, all those numbers that the problem wants to give me, I'm going to write that. That's an equation based on this picture. Oh, I should put this in just a second. The express train, and this is the freight train, right? The distance of the express train is the same as the distance of the freight train. Then I can take this, using the fact that distance equals rate times time, I can blow that out into this, the rate of the express train times the time of the express train equals the rate of the freight train times the time of the freight train. This is important because John's numbers that he gives me are going to be these. He's probably not going to give me this. Every once in a blue moon, he'll play a little trick and give us something like that, but mostly he gives us this. Now that I have my base equation set out, and I don't need to look at the story or the problem numbers to create this. I look at the story, I create the picture, then I can automatically create all of this. Now I know I'm going to need an RE and a TE and an RF, and I'll put the TF over here. Usually I put them all the way down. Now I'm going to go back and see what numbers John gives me. He's not going to give me all of them because I'm going to have to solve for some, but I'll look and see what he gives me. The express train made the trip in 12 hours. So the time of the express train is 12. On Wednesday, the freight train made the same trip in 16 hours. Time of the freight train, 16. Now, it would be very sly of John if he told us like one trip is in this many hours and the other trip is in this many minutes. Then we would have to adjust, right, to make the times the same. But happy spoilers, he doesn't do that. John does not play any tricks with the units, so we don't have to write that down or really worry about it. This is hours, but we don't have to care. Find the rate of each train if the rate of the freight train was 15 kilometers per hour less than the rate of the express train. Oh, we have a balancing statement in this. Okay, let me go back to those words. The rate of the freight train, okay, there's that, is less than, I'm going to change it into an equality, the rate of the express train. The rate of the freight train, I'm ignoring the number, was less than the rate of the express train. The balancing number is 15. This side is too big, so I'm going to subtract 15. And that will make it equal. Aha! Okay, this I don't have anything for, so I will just fill in that blank. I'll just leave it. Before I fill any of these in, though, I'm going to take my base equation and I'm going to rewrite it with buckets. Oh my gosh, buckets are the secret to making this work. Because now we go to our list and we pour in all the information we have to the appropriate bucket. This one we don't have anything for, so I'm going to leave that for now. I'll come back to it. TE is 12. RF equals RE minus 15. That could have been a bigger bucket. It's a little squishy. TF equals 16. Notice how if you write the variables in your list in the same order that they appear, it's really easy to just go through your list and fill them in. Now I'm at the end, I've filled in everything I have. I don't have anything for this one, so I just put the variable back in. Okay? Now, we see we have two variables in here. We know that in order to solve an equation, we have to have the same number of equations as we have variables in order to solve a problem. We only have one equation, but look, it's the same variable that has popped up in here. Now, we have practiced solving from here on out, so the rest of this should look a little familiar. It's the setting up that is new, and that is part of John's genius. He's given us practice already with this. I'm going to rewrite this so that it looks nice. 12 times the rate of the express train equals, and I'm going to distribute this, 16 times the rate of the express train minus, well, let's see, what's 15 times 16? It's 240. And we can do that right here. Right? There's the 240. So we've distributed, and now we're just housekeeping. I'm going to carry this to the top of my next page. minus 240. Okay, that's where we were. I just recopied. Let's subtract the 16. RE, that's going to give us a minus number, but it's okay. That cancels. Minus 4. RE equals minus 240. But once we divide by minus 4, all those minuses are going to just go away. So the rate of the express train equals 60 kilometers per hour. That's just out of the story. And now let's go back and see, because we have to figure out the rate of the freight train. And let's go back here. The rate of the freight train is the rate of the express train minus 15. So if we subtract 15, we'll get the rate of the freight train. And if I wanted to write it out, I could write the rate of the freight train. This is the formula we had. And then I could plug in a 60 here. Right? If you want, I did that in my head. And if you want to not do it in your head, that's how I found this. Okay, we have done our first dirt problem. The second one is one of my all-time favorite, because it drives me mad with curiosity, problems in the book. And there are 3 lessons in all. But this second one just fascinates me. Okay, again, we know that distance equals rate times time, and we know that in these problems, the 2 distances are equal. This may seem kind of meaningless now, but later you'll understand why. It won't always be true. We'll change it up, and that will be interesting. The members of the girls' club hiked to Lake Tenkiller at 2 miles per hour. There's my first question. Is that fast or slow? 2 miles per hour, that seems a little slow. Second question, Lake Tenkiller. Spelled like this. What kind of name is that for a lake? Tenkiller? Did it kill 10 people? Does it kill tens? I don't understand that. I also think of, what is it? It's Lake 22. There's a really popular lake out on the Mountain Loop Highway that I've been on before. It's to Lake 22. And so whenever I am at Lake 22, I think of Lake Tenkiller. Is it the same lake? Did they change its name to protect its anonymity? Okay, so these girls are hiking to the lake. Mr. Ali gave them a ride back home at 12 miles per hour. Who is Mr. Ali? Is he a stranger? Should they be riding with him? Is that safe? Is he someone that they know? Does he work at the lake? Maybe there's a camp at this lake and they hiked out there and now he's like a camp director or something and he gives them a ride back. I don't know. This problem just fascinates me. It's so full of riddles. But when I stop being dramatic and I just look at the problem, I see, oh, these girls hiked to their destination and then they got a ride back from what I'm sure is a very nice man. I imagine him driving one of those big, sort of like a golf cart, only they're bigger, kind of like the things they drive around airports to give people rides. That's what I imagine him giving them a ride in. So here is the distance that they hiked, let's say, and here's the distance that they rode. You get to make up your own letters. You can do that however you want. If you just want to put 1s and 2s in, that's fine. If you want to make the letters match to the story, however you see that, go ahead, do it how you want. Okay, but we can see it's the same distance. So we know that the first distance, or the distance hiking, equals the distance riding. And then we blow that out into rates and times. Rate hiked times time hiked equals rate they rode times the time they rode. This is the one that we'll use as our base equation. Let's make a list of the variables down here, and then we'll go back to the problem to figure out what we know. Then we'll fill in, all right? So we're doing this, I want you to lay these problems out in your homework just the way I show you. Draw the picture, work to get the base equation, make the list of variables, and then here's where we'll do the solving. Okay, they hiked to Lake Tenkiller at 2 miles per hour. Mr. Ali gave them a ride back home at 12 miles per hour. When you hear miles per hour, you always know that's the rate, or kilometers per hour. But that per hour tells you it's a rate. Find their hiking time, that's this, if it was 5 hours longer than their riding time. Okay, so their hiking time was longer than their riding time. This is our balancing statement. Their hiking time was 5 hours longer. So we have to add 5 to this side to get that to balance. And this will just leave plain. Make sense? So we have these balancing statements thrown in these problems too. Write the inequality first, always. Buckets. And now we fill in. And again, I put this in the same order as this, so I can just go straight across. 2. TR plus 5, 12, and then we don't have anything, so again, we just put in the variable. We look, and sure enough, those match. We didn't plan that. That's just how it worked out. Oh my gosh, I love it. And that's one thing I would tell you with all story problems. Don't worry too much about how to find the answer or what answer you want to find. Just follow the steps and do what makes good algebraic sense, and the right answer will make itself shown. I'm distributing now. I'm subtracting, I'm swimming the TR fishies over to the right. 10 equals 10 TR. What? That's easy. The time that they rode is 1 hour, right? Now let's go back and see what John asks us. How far was it to Lake Tenkiller? How far? That's not a rate and that's not a time. That, my friends, is a distance. And that's what makes this such a tricky little problem. Is John's not asking us for the time or the rate. He's asking us for the distance. How do we find the distance? Well, the distance equals the rate times the time. So there's 2 ways we can find the distance. The distance is either the rate of hiking times the time of hiking, or the distance is the rate of riding times the time of riding. We can do it either way because our distances are the same. Oh, this is crazy, right? So what we need to do is we need to figure out if we have the time and the distance for the same part of the trip, right? Whether it's hiking or riding, we need both. We've got the time for riding, and so let's multiply that. It's down here, right? The rate of riding is 12. The time of riding is 1 hour, so that means the distance must be 12. That's the right answer. Now, what if we wanted to use the hiking information to find it? Does it give the same answer? Well, let's look and see. The rate of hiking is 2. The time of hiking we don't have yet, but we can figure it out. It's the time of riding plus 5. So it would be 6, right? So now we can put that over here and look. It gives us the same answer. So the distance equals 12 miles to Lake Tenkiller. And I don't blame the girls for wanting to take a ride with Mr. Ali back. I just hope that they were very careful about stranger danger and didn't take any chances with an unknown adult driving them. Whew, the story has a happy ending though. They got home and we have gotten to the end of that problem. Thank you for enjoying one of my very favorite algebra problems in the whole world with me today. But we have one more. And this one's fine too. It's an Oasis problem. So now we have to get ourselves into desert mode. Think Dubai. Think oceans of desert, of sand in every direction, and listen to the story. Durant drove to the Oasis in 2 hours. Oh, it seems sad there's a road to the Oasis, right? I want to be crawling on my hands and knees through the sand. And, okay, here's the other guy. Medill, he walked to the Oasis in 10 hours. All right. So they're both going to the Oasis. One guy drove, one guy rode. This, we're going to call this distance the first dude, Durant, and this distance is the other dude, Medill. We know that the distances are the same, and we know distance equals rate times time. These are the two formulas that are really driving our work here. Okay, we know they're the same, so we can say the distance of whatever that dude's name. This is Medill. Durant, that's his name. And now we know we can blow that into the bigger base equation that has the rates and times in it. We make our list. And then we throw some buckets at this. Okay, now we're ready. Okay, this was the last time we looked at the problem. All of this we're able to set up just because we know that's how these problems go. That's why organization is so important. That's why I ask you to copy this format, because if you just follow this flow, you'll be all ready now to go back into the problem and figure out what we know. Durant drove to the Oasis in 2 hours. Time of Durant, 2. Medill walked to the Oasis in 10 hours. Time of Medill, 10. How far is it to the Oasis if Durant drove 16 miles per hour faster than Medill walked? Okay, so the rate of Durant is faster than the rate of Medill. And again, we have a balancing statement in our problem. Durant drove faster than Medill walked. Okay, that makes sense. That's what I've written here. 16 is the balancing number. So I have to add 16 and then make that equal. This I will leave just plain. Now we're ready to plug in. RM plus 16, 2. I don't have anything for this. And as I write it in, I just note, oh, look, they match. I'm happy. And then 10. Beautiful. Now we're ready to rewrite it. We'll distribute as we go. So we'll get 2 times the rate of Medill plus 32 equals that. Do some algebra here. Goodbye. 32 equals 8 times the rate of Medill. Divide both sides by 8, and we get that the rate of Medill equals 4. Yay, let's write it over here, 2. Now we can figure out that the rate of Durant equals the rate of Medill, which we now know is 4, plus 16, so that equals 20. We've got all the rates now. I went ahead and found all the answers. You can do that before you look at the problem to see what John's actually asking, or before you go to the work of finding all the answers, you can go back and see what does John want. I kind of like to fill it all in ahead of time because it makes me feel like I've done a complete job. John's question is, how far is it to the Oasis? Again, we remember that the words how far are asking us to find the distance. So again, the distance equals the rate times the time of either dude. So it can be Durant's rate times time or Medill's rate times time. And just like we did for the 10 killer girls, we're going to do it both ways because they should be equal, right? In this scenario, the two trips are equal. So let's see, the rate of Durant we figured out was 20. And his time is 2. So that looks like it's 40 miles to the Oasis. And let's check it if we base it on Medill's trip. His rate was 4. He had to walk. And it took him 10 hours. Oh, look, there it is. So the distance to the Oasis is 40 miles. And just to be super clear, in your homework, you don't have to find it both ways. I just want to show you that no matter which one you choose, you can get the right answer. Doing it both ways is a nice way to check and make sure that you haven't made any little calculation errors, but it's not necessary for the homework. You're doing enough work without me making you answer the question twice. Yay! We're done with lesson 92. We are going to do more of these problems, and in those, the picture will change and the movie will change, right? This is Lord of the Rings. I often call this the there and back again picture because very often, like the 10 killer girls, they did a there and back again, right? Story just like Sam and Frody. Okay, congratulations, you're moving on up. Okay, thank you, goodbye.